we're trying to learn a lot more about at the moment. Clouds are important too because they're rather messy, rather difficult to describe in models. They come in all sorts of shapes and sizes, and they move around, and they're very difficult to get right in models. And they're too, depending on your cloud, you have a different feedback. If you have high cloud, the top of the atmosphere, you get blanketing of the thermal radiation. The radiation from the surface gets absorbed, and it acts to warm the whole system. So that's a positive feedback which is occurring. If you have very low clouds, then the reflection of solar radiation from the clouds loses energy from the system, and that's the dominant effect, so you tend to get a negative feedback. So depending on your cloud, it can be positive or negative. And that may be in different clouds, of course, and appear in different places in different ways, and that's a big thing to take into account too. People who don't understand what we do in computer modelling of the climate are sometimes very rude about it, and say these models are all fudged and they're all, and they imagine they're a bit like economic models and models of human behaviour systems, which are all a lot of guesswork associated with them, and they're terribly rude about the models. Why do we need the models? We need the models because there's no other way to add together all the nonlinear effects you've got. All the equations we have are nonlinear, describing the physical processes, the dynamics and the physical processes occurring. And because they're nonlinear, you can't put them together in an analytical way. You have to compute the effects. We humans can't compute fast enough, begin to compute fast enough to do it. And we have to put, therefore, all of these things in these computer models, which brilliantly add together all these nonlinear processes and effects. And it really is a wonderful tool for doing something which could not be done conceivably in any other way. And a very powerful tool to add it all together. Because you can't, by waving your arms together, you can't say, well, if I increase that, then this will happen, and then that will happen, you think, and then something else will happen, and you think you've got to... But you haven't taken all those non-linear things into account. It's not a linear process. And well, you might be able to make one particular row of things and put it into analytical equations and do something with a nonlinearity, but you can't begin to put them all together in the way you need to do if you're going to describe and model and simulate and predict the climate. How well, if you're going to have a model of the climate, you've got to test it. It's just a single observation or simulation I'll show you. In 1991, Mount Pinatubo erupted and put lots of dust in the atmosphere. The dust circulated around the world. The temperature dropped over a period of a couple of years by about 0.5 degrees Celsius on average. The average temperature of the world dropped by about half a degree. And you can see the simulation there. The observation is the red line, the simulations are the other lines, and you can see we actually managed to simulate that rather as well. So that by simulating events of this kind, you can say, does my model work? Is it possible to predict the future from a model? And this gives you some confidence that you can do things like that. So that's the science of coming from space, observations from space, and modelling from computers, helping you to put the whole story together. Now, of course, these have been very exciting years because of all this new data, all these new computations, all these new people working on it. And meteorology has always been a very internationally organised in very close ways, because we need data from all around the world. You need people measuring things from all around the world. You care about the weather and the climate in all parts of the world. So the whole community has always been together. And so as soon as we began to get this global stuff going, then it was the obvious thing to do were for the organisations which brought meteorologists together and other climate people together would begin to will begin to work together to put their observations together, to put their computations together also, and to try to understand it better. So there's been an enormous growth of international cooperation in this sort of research. Just 2 slides about that, giving you a list of things. The organisations which have got together over the years, since the 1960s, the World Meteorological Organization joins meteorological services together around the world. International Council for Science joins scientists together around the world in an international way. International Oceanographic Commission joins oceanographers around the world in a very active manner, in the United Nations Environment Programme, trying to sort out the environment for the world by the United Nations. All those bodies got together to generate certain programs. In the 1960s, we started the Global Atmosphere Research Programme. We could see the global atmosphere for the first time. Observations from space of the kind I showed you, of the kind we were making in Oxford, could be put together, and we could try to study the whole world all the time. And it was people like Professor Berlin, and Professor Bert Berlin was a very remarkable Swedish man who pioneered a lot of this international cooperation, but not just him, lots of other people too, got together in the Global Atmosphere Research Programme, which lasted during the 70s very largely. And then the World Climate Research Programme in the 80s, and still going on. I was privileged to be the second chairman of that programme, and with Pierre Morel from France as the director of that programme, and we set up things like, there were big programmes like the World Ocean Circulation Experiment, TOGA, Tropical Ocean Global Atmospheres Experiment, and so on. Lots of different experiments within those programmes have moved this forward on an international scale by getting scientists together, working together around the world. International Geosphere Biosphere Programme was another one largely set up by ICSU. And then, of course, the IPCC, I'll say more about that in a minute. And then finally, the Global Climate Observing System. In order to observe the whole climate, we have to put all the data together. And how do you do that? Coming from all sorts of sources, from space, from ships, from buoys in the oceans, from things under the ocean, from the land. All this data has to get together somehow in order to provide very large data sets. And how do you do that? And the Global Climate Observing System, which I had a lot to do with its foundation, and I was the first chairman of it, started in 1992. A very difficult thing to do because it's so big, and it's still blossoming on in the way it's doing things. So that's the research work. Now, the big question we want to know, are human activities changing the climate? A very big question for the world at the moment, as you'll all know, coming to a head in Copenhagen in a couple of weeks' time. Going back to, Claude Monet came to London the early 20th century and painted pictures of London. And he loved London because of the light coming through the smog. He must have had a very good nose, because it must have been an awful place to live in. And that's local pollution. That's how London was polluted. Terribly polluted in those days. Still is polluted, but it wasn't anything like as bad as it was then. And that's pollution that occurs because of the people in London were putting smoke up out of their chimneys, industries were putting smoke out of the chimneys, lots of other polluting sources, so they were having to live with their own pollution. Local pollution. We now have examples of global pollution. One is the ozone problem, but the one which I'm concerned with here is the increase of carbon dioxide, because we're all burning coal and oil and gas, or causing it to be burnt, increasing the carbon dioxide content of the atmosphere, and we're all doing it. Everybody on Earth is contributing, either directly or indirectly, to that problem. Carbon dioxide lives in the atmosphere for typically 100 years. It's a very complicated lifetime. And so all of us are contributing to global pollution. There's no doubt about it at all. We're all guilty of contributing to this problem. And the global problem demands global solutions. Very quickly, I'm now going to try and tell you very quickly the science and the impacts